Now that we have the model simulation code in a separate function file, we are ready to run an experiment. And we're going to start with a fairly straightforward experiment that's often done both in computational neuroscience and also in empirical neuroscience. So the idea is to inject an increasing amount of input into the neuron and record the number of action potentials that the neuron emits in response to that input. So this thing is called an FI curve. The F stands for firing rate and the I stands for input current. So the way that this experiment works is that we simulate the neuron for 500 milliseconds, just like we've done in previous videos, except now the input strength is going to be constant. So we're going to have a constant strength of input into the neuron over time. That's different from 2 videos ago where we changed the input strength to be 0. And then between 100 milliseconds and 400 milliseconds, it was, I forget what value we used, but it was some non-zero value. And then after 400 milliseconds, we went back to 0 input. So in this experiment here in this video, we're going to provide constant input over time. Okay, so then the output of the function is the membrane potential voltage trace, and that you see in the black line here. So then what we want to do for this plot is count the number of action potentials, and that's indicated by these red dots here. So we need to find all of the action potentials in this time series and then plot a little red dot where those action potentials occurred. Then we count the number of action potentials that occurred in this simulation, and that goes into this plot for, whatever input current this was. Now notice the y-axis here. This is in units of spikes per second, but we are running this experiment for 500 milliseconds. So you're going to need to convert the data, so the number of action potentials, from the count of action potentials to spikes per second. Okay, so this procedure that I described, so running the simulation for one input strength, get the spike rate, convert it to spike count, or spikes per second. That gets repeated for a range of different input values, starting from 10 picoamp up to 600 picoamp. And I believe there are 20 steps in between 10 and 600. So from me describing this experiment, you can see the advantage of having the simulation in a separate function file. So we need to run this simulation 20 times, which means we're running the identical simulation code 20 times, only changing one parameter, which is the input strength. Now, of course, you could do this in a loop. You don't necessarily need a separate function file, but you can already imagine, and you will see in a few moments in the code, that having the simulation be in a separate function file makes the analysis code more compact and easier to work with. All right, so now let's switch to MATLAB and get coding. So the file that we are going to work with here is called adexspike.mlx. So you can see this is also a MATLAB live script. And in fact, by looking at it, you can see that there's already quite a bit that I have done for you, including setting up all of these parameters here. I even got all the spaces to look nice, so it's all nicely vertically oriented. This is important for visual readability of your code, to have nice visual layout of the code. Okay, and then I already have a bunch of parameters. These are, of course, the same parameters that we used in the previous videos in this module. Okay, let's see. Then we have some time parameters. The input current, notice here this is fixed. Now what I want to do is, again, just look through the entire code file and try to get the big picture sense of what's happening in this file when. Now I've already mentioned that it's a good idea to do that several times before, but the point is that it's a good idea to do this all the time when you're looking at anyone's code, not only for this particular course. Okay, anyway, so then it says run the simulation. Now here we're not actually, there's no for loop that goes over the different input strengths. So I believe that here we just want to run the simulation once. And then we're going to get a result, and then we are going to make a plot. So one plot of the membrane potential and the action potentials plotted on top as red circles. I'm also going to show you how to export your figures as files, so a PNG file and a PDF file. So we'll get to that in a few moments. Okay, then here's the code for the main goal of this experiment. So we run the simulation for various input strengths. Here we define the different inputs. We're looping over those inputs. And here's where we need to write a little bit of code to run the simulation, find the peaks, so the action potentials, and then do some conversion. Looks like there's something missing here. And then finally, we make a plot. Okay, so now we have like the big picture overview of the code. So let's go back and start inspecting it in more detail. So everything is done for us up here. So I'm just going to click inside this cell and press Control Enter. Very nice. Now, you know, this code doesn't do anything. It doesn't run any simulations. It doesn't generate any plots. So I'm not expecting anything to happen except the absence of error messages. So we don't see any errors or warnings. So that's a good sign. Okay, so now we need to run the simulation. So I'm going to use the function that we created in the previous video. Remember, that was this file here. I saw this open. That is called function mempten simulate AdEx, and then the input is params. Okay, so let's run this. We need to call the function, so simulate AdEx, and we only need to provide one input, which is the list of parameters in this structure that we create up here. Okay, so let's run this and hope for the best. Uh-oh, we get an error message. This says index exceeds number of array elements. And now we can actually click on this line number here. This is a hyperlink. We can click on this, and that's going to open up the file. It's already open, but if this file weren't open, so I'm going to close it now, we can click on this line number, and MATLAB will open up the file and take us directly to the line that caused the error. So what is the problem here? Well, the issue is that we are trying to extract multiple indices from this parameter here, params.input. Now, in previous videos, that was actually correct because we had time varying input. So we had one input value for each time point. However, the way we have it set up here, we only have one value for the input parameter, and that value is constant over all time points. So that's why we're getting an error. We are trying to extract the second element from an array that has only one element in it. Now, there are several ways that you could go about fixing this error. One thing that we could do is just delete this. So just have this be in equals params.input. The thing about this solution is that that's going to work for this code here, but it's actually going to break our previous code. So we had this in part 1. Now the input is a vector. And here, this really needs to be a vector. So if we were to delete this here, then this would cause an error. Okay, so let me undo this. So in this case, it's fine because we have this code separate in this code file and this code separate in this function. Another way we could have addressed this is by leaving this as a vector the way it was, and then we could change this. So this, instead of being a scalar, a single number, this could be an entire vector for however many time points we have, and every single time point is equal to, in this case, 500. So either one of those solutions is fine. I'm going to do the easier solution here, which is to just delete the reference to the elements in this input matrix. But the reason why I did that, and the reason why I wanted to discuss this, is to give you a sense of how things can start getting confusing and possibly causing errors in MATLAB. Because if you are changing things in functions, and then different scripts that are calling those functions are expecting the function to behave in different ways, that can either give you incorrect results or it can give you errors. Okay, so all that said, now we fixed it here, so it's going to work fine here. Now, what happened here? Well, you know, we need an output, right? This file gives us an output, which is the membrane potential. But we're not actually calling that output or assigning that output to a variable. So I'm going to use this variable name here, so memvolt equals, and now I run this cell again, and now we see that this vector memvolt has a bunch of values. In fact, it's 50,000 values. Okay, so now we need to plot the result. Let's see, we need to find the action potentials. I'm going to turn this off. I'm going to comment this line out for a moment and also comment this line out for a moment. And that's just because I want to make sure that we really got a valid result. So I'm going to run this cell, and we see, as expected, we get a very nice looking plot, just like what I showed in the slides a few moments ago. Okay, so now let's identify all of these action potentials here. So the action potentials are easily identifiable as the peaks of these traces. So therefore, we are going to use the MATLAB function find peaks. So we need to input the membrane potential that we got, the output from this function. And then I'll just run this again before worrying about plotting, just to mouse over this thing and make sure that we get a result. So these are the indices of all of the action potentials. They don't tell us the peaks, the actual y values. That would be in the first output, which I've suppressed here. Actually, we can run it again just so you can see what they are. The thing is that these are all going to be zeros, and the reason why the action potential value, so the membrane potential is 0 at all the action potentials, is because, well, it's because that's what we set them to be in the code. Okay, so therefore, we don't actually need this value, so I'm just going to suppress that first output by using a tilde instead of a variable name. Okay, great. So now we want the red circles, so let's uncomment this line and see what happens. We get another error, something about that. So let's see, the plot says vectors must be the same length. So that means that the x values and the y values are not the same length. Well, here we have the spike locus, and it looks like this vector is 24 elements long, and that seems pretty sensible. You know, it seems like there could be 24 of these action potentials. But this variable, which is the y for the plot line, is the membrane potential. It's 50,000 points. So in fact, what we want is the membrane voltage potential, but not the continuous voltage potential, but instead only at the time points corresponding to the spike locus. Okay, so these are the indices. These are the values. Now, of course, you know, previously I showed that we can get the first output of that find peaks function, so we could have also done it like this. But I like how this looks here. Okay, so let's try running all of this code again and hope for the best. Well, hope only takes you so far. You still have to have accurate code beyond just hoping that it's going to be correct. So what is the issue here? It looks like these spikes are misaligned. They're going all the way out here to like a really, really large value of time where we didn't even record data. You know, we didn't simulate data this far out. So what's the issue here? Well, the issue is that we are plotting the spike time indices, but actually we want the spike times in milliseconds. So just like we did here, we need to say that we want to plot not the indices of the spikes, but the time points at which those indices occur. You can see why I like doing it this way. It has a nice symmetry in the line of code. Okay, so let's run this again, and I think that, yeah, so now we actually got it correct. Okay, so what I wanted to do now is uncomment these lines, and this is really simple. This is just showing you how to export this figure, and I'm going to export it twice, once as a PNG format and once as a PDF format. So again, I'm going to run this cell by pressing Control-Enter on the keyboard. And we can see, so these opened up on my second monitor. So here is the PNG file. And then here we have the PDF. Okay, so nothing, you know, terribly earth-shattering about this, just to give you some code that will allow you to spit out these plots to files. Okay, very good. So now we are ready to run the actual experiment. Here we have the various input strengths. We are initializing the output. So this is spikes per second. This is going to be the main dependent variable that we are going to make a plot of. Okay, so we loop over all of the inputs. And what do we need to do? Well, we need to, so let's see, I'm just going to copy and paste this code because I know that this works. We spent some time working through that. So we want to run the simulation. However, if we just leave the code like this, then, well, it's not a very interesting experiment because we are using the same input strength over and over and over again. So what we need to do is reset params.input to be the inputs, so inputs and this particular value corresponding to this iteration over the for loop. So we don't have to update all of the parameters, we only update the input parameter, and then we run the experiment again. Here you see we are using find peaks. We are inputting the mem volt, so the membrane voltage potential that we get the output from this function. And here I've added another optional input into find peaks. And this is just a bit of FYI. So here we're saying that the min peak height must be equal to minus 20. So that means that if there's any local peaks, so local maxima that occur down here, those would not be counted as action potentials. A peak here would have to be at least minus 20 in order to be counted as a peak. Now, for this particular simulation, this is a noiseless simulation, so we don't need to worry about that. But you can imagine if there were a little bit of noise, if we're simulating a noisy input, you might see that the local membrane potential might go up a little bit and then go back down. And that would just be attributable to a bit of noise. It certainly isn't an action potential if there's a tiny little bump like an EPSP coming in over here. Okay, so so the MATLAB find peaks function is quite powerful and flexible. So there's a lot of optional inputs that you can explore. Okay, so now here we have the number of spikes in 500 milliseconds, and the question is, how can we convert this into spikes per second? Well, one thing we can do is, we know that we are simulating the data for 500 milliseconds, so we can actually just multiply it by 2, and this would give us spikes per second. Now, that's fine, but I am not really happy with this solution. And the reason why I'm not really happy with that is because, let's say you simulated a different neuron that had a much slower firing rate, so you wanted to extend the simulation time a little bit. So extending the simulation time is really easy. You can just set simdir up to, we can simulate for like 2 seconds, for example, 2000 milliseconds. But then if we still keep this fixed hard-coded multiplicative factor of 2 down here, then now this isn't spikes per second, it would be spikes per 4 seconds. Okay, so what I am going to do is replace this with params.simdir divided by 1000. So params.simdir is currently set to 500. I changed the text to 2000 a moment ago, but I didn't rerun that code. So it's still set to 500, which is what we want. And then 500 divided by 1000 is going to give us 0.5, which is basically the duration of time in seconds. So this is really just converting it into seconds for the simulation duration from milliseconds into seconds. And then we are dividing by the simulation duration in seconds. So now if you change the simulation duration, we still get the result, the number of action potentials per second. Very nice. So I'm going to now run this code. I hope it's all correct. And that's all fine. So now we can plot the Fi curve. So we plot the input strengths by the vector of spikes per second over here. And yeah, just a few other niceties to make the plot look a little bit nicer. Let me open this up as a new figure. Make sure we're plotting this in a new figure. Okay, here we go. And I'm going to put this back to a figure on the right because I prefer this output. Okay, so there we go. We get our Fi curve, which looks pretty similar to what we saw in the slides. By the way, it's pretty interesting to see that although this Fi curve is generally going up, it's not a perfectly linear function. So we get some flat lines here, which is actually not attributable to noise. And that's because we don't actually have any noise in the system. So the fact that these two inputs are giving us the same spike count, and these two inputs give us the same spike count, is telling us something about the neuron. And basically what it's telling us is that, there's these gaps between the bursts of action potentials. And depending on the duration of the experiment and the characteristics of the neuron that define how long this burst is going to be, you have two separate input strengths that actually have the same effect on the neuron in terms of the total number of action potentials within this time window. So I hope you found this experiment pretty neat. Now that you have this code, you can start to explore lots of other things, lots of other dynamics in these AdEx neurons. For example, you can change the inputs from being constant to time varying. You can make the inputs be sinusoidal or noise or triangular shaped. You can try changing all of these parameters to see what effects that has. So how different kinds of neurons will behave in the same experiment, and so on. So that's the end of this video and the end of this module on computational modeling in neuroscience. I hope you enjoyed it. I hope you found it interesting. We covered quite a lot of topics in neuroscience and also many new topics in MATLAB, including live scripts and translating differential equations into MATLAB code.